Find the shortest distance between these two curves. Nice question. I'm going to sketch the first one out, y equals x cubed plus 4. So that is going to end up looking a little bit like that because it's like a y equals x cubed curve that's just been translated by 4 in the y direction. So I know this is 4 here. And then I've got y equals 2x minus 2. So that's going to have a y-intercept of minus 2 and a gradient of 2. No, they're never going to meet because the quadratic, I mean, you could investigate that, I guess, but we can see it's like quite far below, and then this one is just going to get steeper and steeper. I suppose, maybe it is good to just test that. X squared plus 4 equals 2x minus 2. X squared minus 2x plus 6 is 0, and you'll very quickly get a discriminant that's, you can complete the square and show there's no solutions or show the discriminant is less than 0. And it's, there's no 0 in the answers anyway, but it's just good to think about. So we want to somehow find this shortest distance, and we don't have any points or anything. So I'm going to pick a point here and a point here. Note that the shortest distance from a point is going to be at 90 degrees. So that there will be 90 degrees. I'm not going to go off down there. I'm definitely going to hit that blue curve at 90 degrees. So we can write down the coordinate of the red curve. If I just say that the x coordinate is a, then the y coordinate would be a squared plus 4. And for the other curve, b, and then 2b minus 2. So I need to find the distance between these and minimize it. In fact, I can look at the distance squared. That's the best thing to do because then I can just be applying Pythagoras' theorem. So I will get b minus a all squared. That will be the horizontal distance plus 2b minus 2 minus a squared plus 4. So I can just write that as minus a squared minus 4. And then remember, I'm squaring it. So I found now the vertical amount, and I've squared it because we're applying Pythagoras to work out this d. So this is going to simplify a little bit, but it's also looking very awkward. Because there are two unknowns. So we do not want to be doing any kind of, calculus with two variables. That is not on the A-level syllabus, and there's a different approach is needed. There's more than one approach. All of them are going to be complicated. This, I think, is the hardest question in the paper. You may disagree, but that's my view on it anyway. When I saw this, I was like, I'm not really sure what to do here. But what we can do is the following. We can actually imagine moving this blue curve. Actually, I'm just going to make a second copy of it. I'm thinking, where would it hit? Because we had that 90 degrees on where the blue curve is. But if I make it hit here, then again, it should be that actually this becomes a tangent. It must be the point that it just touches, it's a tangent. And that is actually the crucial way to answer this question because we can work out where they have the same gradient, and hence we can work out this point here. I do not think that's obvious, personally. So let's differentiate y equals x squared plus 4. I'll get dy by dx equal to 2x. I'm going to set it equal to 2, the gradient of the blue curve. So x is equal to 1. And that, now I remove this one, that actually tells me this point here. It's going to be not a squared plus 4, but 1, 5. I'm not going to do the whole thing again, though. I'm going to take my d squared and now sub in for 1, 5. So I will get b minus 1 all squared plus, then it will become 2b minus 7 all squared. That is my distance squared. I still then got to minimize this. Notice I'm minimizing d squared. I'm not going to bring the square root in, but we will square root at the very end. We're going to get a quadratic in b. So b squared minus 2b plus 1 plus 4b squared minus 28b plus 49. That's going to give me 5 b squared minus 30b plus 50. Factorize the 5 out. B squared minus 6b plus 50. Okay, complete the square. You could differentiate with respect to b. Nah, let's complete the square. B minus 3 squared minus 9 plus 50. So I'm going to get, oh, sorry, that's still inside the bracket, isn't it? So 5b minus 3 squared minus 45 plus 50, so plus 5. Because we know that that point there, we didn't just then immediately know the b 2b minus 2, although we could have maybe found the equation of the normal and looked at where it hit it and worked out that one and then done Pythagoras from there. Hey, I think that would also work and maybe a little bit simpler. I might do that in a minute. But the minimum of d squared is therefore going to equal 5, and therefore the minimum of d is going to equal the square root of 5. So our answer is B. So let me just summarize what we've done. We've drawn the two graphs out and we're trying to find the shortest distance. So I just picked x equals a and x equals b on the respective curves, wrote down the y coordinates from knowing the equations of the curves, then worked out the distance between these two coordinates in terms of a and b. That did not look like it was very nice, so we did not pursue that further. Instead, thought about the problem, the fact that we are going at right angles to the blue curve, but actually, more importantly, we'll use that in a minute, but actually this blue straight line, I should say, would be a tangent to the curve where they meet, if I imagine just translating it. So I can find out that coordinate there, because as I move it, it would still be, the point at which to find the shortest distance by differentiating and finding where the gradient is equal to 2. So we've got x equals 1, we worked out that coordinate, we rewrote d squared just in terms of b, expanded it, got it as a quadratic, completed the square, and hence minimized it. Notice I minimized d squared, and then I square rooted to get d. Yeah, so it's pretty complicated. What was I going to say? Just that, we still have to minimize it in terms of b because we just didn't have that coordinate b 2b minus 2. Now we could actually find b 2b minus 2 and then do the distance from the beginning using these ideas. And actually, in hindsight, that would be the quickest way to do it. So you can draw the curves out, realize that we've got 1, 5, and then actually work out b 2b minus 2 by finding the equation of the normal to what we would have had as a tangent. So you're going to get a gradient of minus a half for the negative reciprocal, and then we would get, I'm just going to go with y equals mx plus c here, but y equals minus a half x plus c. This is going to be the normal now. And then I can sub in 5 and 1. So 5 equals minus a half plus c. So c is 11 over 2. Then I can set that minus a half x plus 11 over 2 equal to the 2x minus 2. That will give me this point here. That's the one I want. So I will get 5 over 2x equals 15 over 2. X is equal to 3. That's actually my value of b, by the way. So y is then going to equal 4. So I've now got the coordinate 1, 5, and I've got the coordinate 3, 4. And I can find the distance in between. So I'm not like minimizing the distance now. I've just used the fact that they are going to be at right angles. That's the key idea here. So I'm going to be going down by 2, along by 1. 2 squared plus 1 squared is 5. Square rooted also gives us that root 5. Wowzers. Well done.